Okay, so I'm going to review questions 1 and 3 if you're having trouble. And if you follow what I'm doing here, although I'm going to complete the problems till their entirety, stop the video and continue on. So if you're having trouble starting or you're at a certain point you don't know what to do, listen to my video, stop it, continue on, and then come back to me and hear how I finish this off, and that might be very helpful to you. Don't want you just watching me do this. I want you to struggle a little bit first, okay? So in any case, I got a sealed flask, so the first thing I do is I draw when I can. So I've got a flask or a container, and I guess my containers aren't that fun looking, so I'll draw myself a little rectangle here. And I know that I have 3 liters of hydrogen. Again, these liters I'm giving it to you, it's kind of like that demo I did today where we're injecting 3 liters of hydrogen into this container, because once hydrogen gets in the container, it fills the entire container. So I got 3 liters of hydrogen. I'm going to put this line here to show you that proportionate amount. I've got 2 liters of CO2, and I'll put that a little smaller. And I have some unknown amount of chlorine. Okay, and that's my setup. So I know that the partial pressure of carbon dioxide is equal to 200 torr. Okay, well, first and foremost, since these gases are in the same conditions of temperature and pressure, they're in the same container, then I know that volume is proportionate to the number of particles, proportionate to the number of pressure, or the pressure it exerts, because if particles differ, the pressure will differ exactly by the particle differences, because it's what the particles do to create the pressure, which is collide with the container walls. So I'm looking carefully at this, and I see that 2 liters, okay, and 3 liters differ by a certain amount. So I'm going to do it this way. So I noticed that hydrogen, okay, and I want to find the volume of hydrogen. Well, I know that if I have hydrogen, and I know I want the pressure of hydrogen, sorry. So if I start with hydrogen, I see that the volume is a certain amount. Okay, how much larger is hydrogen? Well, there are 3 liters of hydrogen for every 2 liters of CO2. So that, if you put that in your calculator, if you don't have to, it's good, it's a 1.5 difference. So hydrogen has 1.5 times the volume of CO2. So shouldn't it have 1 times the pressure if they're in the same container of CO2? Absolutely. So what's 1.5 times 200? Okay, so if you need to write that down, 200 torr times 1.5, and you'll get 300 torr. And that's how I solve for the partial pressure here. Now you say, Mr. Grodsky, all right, how else do I do this? Well, I know that the entire flask is based at STP conditions. Now STP Standard Pressure is 760 torr. It's something we should know already. Same thing as millimeters of mercury. So I know that 300 plus 200 is 500. So 760 minus 500 torr, okay, give me what? Give me 260 torr. And now I know that this is 260 torr. Now that's not what they asked for. They want the volume. Okay, they want the volume. Now I don't know what the total volume is. Okay, that's important you understand that. I don't know the total volume. But I do know that I have a what? I have a proportionality here, right? If carbon dioxide is 2 liters for 200, Cl2 is 2.6 for how many liters? Maybe you see that already, maybe you don't. So let's get rid of some things and see if we can figure this out. Now if you look carefully, look at H2 and CO3. There are 3 liters contained total. 3 plus 2 is 5. 5 liters. Wait a minute, and the 5 liters these guys take up, they exert 500 torr. For every liter, there's 100 torr. So that should also clue you in that this is 2.6 liters. But if you don't see that, remember, pressure ratios and volume ratios have to be proportionate if gases are acting the same because they're under the same conditions of temperature and pressure. So I take my 260 torr, okay, of Cl2, and I divide it by the 200 torr, okay, and what you're going to get is, 1.3. It differs by 1.3. Wait a minute, 1.3 times, right? So that means that this gas has more pressure than this gas by 1.3 times, which means it should have a what? A volume, right? A volume difference of 1.3 times. So take this 1.3, or take this ratio, and times it by what? By 2 liters. Look what I did here, guys. I times a ratio of pressure to get a volume. Notice the torrs cancel. So 1.3 times 2, you get 2.6 liters. Look what cancels. Torr goes bye-bye, you're left with liters. And the answer is 2.6 liters. So just to backtrack, okay, I was given this value here, and I saw that, and did I have to go this route? Yeah, for me, I had to figure out what the pressure of this one was. I knew the total pressure was 760, so I knew that 3 over 2 was a 1.5 difference. And you notice I could have cleaned this up. I could have taken this 1.5 difference and then times it by what? The 3 over 2 liters of CO2. Look at this ratio. This fraction of liters, okay, would give me, oops, bad Grodsky. This fraction of liters times it by the pressure, sorry. The pressure here would be 200 torr. Torr of what? Torr of what chemical? CO2. Now watch, party people. The CO2 cancels. The liters cancel. And 1.5 divided by 2 times 200 would give you the 300 torr of H2. Okay, so there's many ways to think about this, but either way, look at this. I'm using volume fractions times a what? A pressure to give me my volume relationship or relative here. Here I used pressure fraction times a volume to give my volume relative to that. So in any case, important you see that a volume fraction or a pressure fraction could have been used here to solve this. All right, and you needed both things to do in order to get total pressure. Because once you had the 500 torr and you knew the total pressure from STP, that 260 came into play, and then you could use your what? Your pressure. Okay, so it's important you understand. Kind of a little difficult type of a question here, but you think about these relationships that are proportionate. It's a very good problem. So let's go down to number 3. Oops, let's erase number 3 first. In number 3, I have 3 gases in a container, so let's draw. Okay, here's my fancy flask. And I have nitrogen. I have 5.10 grams of nitrogen. You can mass out a gas. I have no idea what the volumes are. I'm just going to put them in here, but understand these lines don't exist. I probably shouldn't draw them. Some purists are probably yelling at me, but 2.83 grams of H2, and then I have 5.17 grams of NH3. Obviously they're filling the entire flask. I'm just putting in here to show a partition of each one. Okay, first step, party people. We want to take these grams, which are useless to me, and convert them to how many? Because remember, We have gases in a mixture under the same conditions of temperature and pressure. What's proportionate is moles, volumes, and their pressures. Since I'm looking for the partial pressure and only given the total pressure, PT, total pressure is 2.35 atm, I don't know what to do with this yet. Okay, so if I take this total pressure and times it by a fraction, I can find the individual partial pressures, right? All the total pressure, this partial pressure of N2, this partial pressure, and this partial pressure have to equal this. Remember, Dalton's Law is pressure total equals the partial pressure of N2 plus the partial pressure of H2 plus the partial pressure of NH3. All right, so here we go. First step, well, I need volume, so I can convert this to gas at STP maybe, or PV equals nRT and solve for liters. A lot of work there, okay? Or I can convert to moles. So let's do that. So 5.10 grams of N2. I'm going to convert to a how many, from a how heavy to a how many number. I get rid of grams, grams go below, and 1 mole, because we're being cool, we're taking away the E. Now, you should know that each N on the periodic table has an atomic mass of 14. That's a relative atomic mass. It's based really upon the smallest one, which is hydrogen. So nitrogen is 14 times more massive, but we know a box full of nitrogen at 22.4 liters is 14 grams. And we know that a box is a certain number of gas positions or seats in the theater, but there's twice the N here per seat. So this has to be 2 times 14, which is 28. We call that a molecular mass. Okay, grams go bye-bye, and let's come up with a value for moles. 5.10 divide by 28, and I get 0.182. And that's moles, okay, of N2. Okay, next one, we have 2.83 grams of hydrogen. Same understanding, H has atomic mass of 1, but because it's diatomic like nitrogen, there's 2 of them per seat. So a mole of H2 is 2 moles of these atoms, and each one of these is 1 gram, so this is 2 grams. Okay, 2.83 divide by 2, and I get 1.4, 1.5 moles. Not worried about rounding here. Then I take 5.17 grams of ammonia, 1 mole of ammonia. Well, 1 N per seed is 14, but there's 3 H's there. Each one is 1, so 14 plus 3 is 17 grams per mole. So 5.17 divided by 17, and I get 0.3041, we'll call it, mole. Now what I'm going to do here, party people, is find total moles. Now why am I going after total moles? NT I'm going to call it. Well, I'm trying to make a mole fraction. Fraction of the moles. Moles represent the actual number of gas particles. I have a fraction of the pressure, right? So let's add them. I'm pretending I could hear you. Plus 1.415 plus 0.1821. Add them together, assuming we carried the same number of digits here, 1.9012. That's total moles. Now how do I get a mole fraction? Part over total. So let's take this mole. We're going to divide it by the total moles, which is 1.9012. And we're going to take this and we're going to times it by the total pressure. Whoa, why does that work? Why does that work? Now this is mole, and the moles cancel. Now sometimes you'll see it written this way. A mole fraction could be X, or sometimes they call it chi. X to the N, for N2 would be the mole fraction. And I can actually find this number. For instance, you would say 0.1821 divided by 1.9021. And this would give me, when I divide by this number, the mole fraction chi N2 is 0.0957. It doesn't have any units because the moles would cancel. And that's the fraction of the moles. So you can actually solve for that and then times it by the actual total pressure. Remember, the individual partial pressures equal the total, but the fraction of the partial pressures have to be the fraction of how many particles you have, because each particle collides. What makes the pressure is a number of moles, so they're proportionate. So in any case, multiply your fraction of moles must be the fraction of the pressure times that fraction by the total. And we get, I just erased it, so bear with me, okay, or pelican with me, divide by, what do we pick bear? I guess I don't know. Divide by that, so I get 0.095 times by 2.35er, and I get a partial pressure to be 2.25, and we just found ATM. And that can't make, 0.225 ATM. I'm just going to say that didn't make any sense. All right, next up, I'm going to divide by total moles, 1.9012 mole. We're going to times that by 2.35. We're going to take that mole fraction, which is a fraction of the moles, and here we go. 1.415 divide by 1.9012, and I get 0.744. That's the mole fraction. Take that fraction, times it by 2.35, and I get let's do it in red. 1.75 ATM. Back to blue. Okay, this is going to be over 1.9012 mole. As we talked about before, the moles will cancel. Mole fractions are dimensionless units, and we're going to times that by 2.35. You should see the pattern here. So what we got? 0.3041 divided by 1.9012. The mole fraction is 0.1995, but we just take that number, whatever we get, times it by the total moles to find the fraction. And we get, in red, 0.37, and we'll do 6 here. And that's, of course, ATM. Just for fun, even though here's your answers the mole fraction of nitrogen, here it is. The mole fraction of hydrogen, there it is. Mole fraction of ammonia, NH3, there it is. Okay. And just for fun, what's the total? Let's add up these entire moles, 0.225. Let's add up the entire partial pressures and see if in fact they add this up. So yeah, for N2 it's 0.225 ATM. Partial pressure of hydrogen, 1.75 ATM. And the partial pressure of nitrogen, 0.376 ATM. And what do we get, party people? Let's see. Add these up. And I get, believe it or not, wow, 2.351, which would round off to 2.35, which is what we got for the total. So the individual partial pressures, okay, equal the total. And that's an application of Dalton's Law of partial pressures. Okay, now the reason why that I'm a little bit off here is because of how I rounded through this problem. Okay, so that's the two questions in their entirety. And again, you should not just watch me do this. If you just watch me do everything, then take a fresh, clean piece of paper and do it from scratch. You have to understand the core principles in these problems. Okay.